All right, Chips. So, last video I said, hey, here's how to do a regression. I didn't really explain all the lines very well, but you could literally see them on the board. So I thought you guys can work it out. What I didn't really do though is I haven't really talked about the underlying statistics. So I wanted to do a quick note on that and what's really going on, because I really kind of glazed past that, which isn't really great if you're wanting to actually investigate things. So let's talk about what I was meaning. So normally, when you've got things, they're distributed normally. And what do we mean by that? We mean that typically they might have this shape. Now, not everything has exactly this shape, but a lot of things in the world have this kind of distribution. So you've got some kind of average value up here. So it's or rather say here is the average value, and it's very frequently. This might be, say, the frequency at which things occur. And then the further away that you get from the average, the less and less frequent that these values get. So an example is height, right? Like there are a lot of people, there are a lot of men who are around 5'10". And that's great and everything. And then you also have quite a lot of people who are 5'11", you have quite a lot of people who are 5'9", 5'8". And then once you start getting to the 6 foot and the 5'7", it's a bit rarer. And once you get to the 6'3" and the 5'5", these are quite rare heights. Meanwhile, the Americans are clueless, but that's okay. So that's a terrible normal curve. So a lot of things like height follow distribution like this. Sometimes you get things that are a bit skewed like that or like that, so that it might not always be completely even. And obviously there are a lot of things in the world that aren't exactly normally distributed, but a lot of things are. And the same can be said of when we're trying to take estimators. So first of all, how do I find an estimator? And then we're going to go back to the variance, how they vary. And trust me, it's all going to link together. But it is a lot to take in. I'm wanting to do a sort of crash course. So let's say I've got two things. I'm going to call them T and Z. And I want to see how they're related. So I want to try and they're data points that are dotted around. And I want to try and find the line of best fit. I want to try and find what captures their correlation. And also, if there's nothing else affecting either of them, that's like having a joint effect on this and on this at the same time, then odds are whatever line best fits all these data points is how much one is causing the other. Reflects some kind of true relationship between them. So I want the line that minimizes deviations. So what I mean by that is I want the line that will give me kind of on average the smallest distance from the line to the different data points. The line that most closely fits the data that we see. And so I do a formula for that. I'm going to say, hey, I want to find values of some kind of estimators that minimize deviations from my different points of t, from my values against z in this case. And I want to square that. So this is the sum. This is all of the values added up. And I want to square that because I want to make sure that they're all positive. That's the simple way of explaining it. It also has a weighting value as well, right? Because a deviation that's very big will show up bigger than a deviation that's very small. A deviation that's like 10 squared is 100, 2 squared is 4. So by squaring it, I also make small deviations not counted as much as big deviations. when I'm weighting it up, which is cool. But the other value is that if there's a negative difference, I square it, then it's weighted the same as an equal positive difference. So I don't need to worry about, oh no, this isn't you know, I'm going to take things away from each other and they're going to cancel out. That's not going to happen with some squaring. So what we then do is we then do some calculus to work out, okay, well, what values of B0 and B1 mean that on average, this is as close to this. That's the intuition of what we're doing. So we're trying to find some values and of these that will best fit the data of my t and my z in this case. And where b0 is the underlying constant and b1, it's the amount that I'm timesing, in this case, z by. So b1 is going to be the gradient of the line of best fit, that minimizes the deviations from the data points. That's what we're doing when we're doing a regression, and we're chucking it in. We're chucking in these values. This is what it's trying to do, and it basically takes all these points and does this for us, because obviously we don't want to look at 500 different data points, manually look at these differences, try and do some calculus to find the values that would make it best fit. That's a lot of work for us to do by hand every time. So instead, we can just chuck it into the software. And that's great for us. We're very happy. But how do we then interpret it? Because then we're going to have these estimators. So typically, we would call them b hat 0, b hat 1. This is a simple regression, right? Because I've just got one variable that I'm comparing to a dependent variable. I've got these estimators. In the last video, they were called the estimates in the estimates column. And I want to see, well, how do I interpret them? Well, the problem I've got is that if I've got loads of data, which has a lot of randomness involved in it, because there are a lot of random things in reality that affect stuff, other than just, so let's say I was looking at whether you had a gene and whether you were a certain height. Well, that might be interesting to investigate, but there are going to be lots of other things affecting your height. There are going to be lots of other genes. There are going to be the things you ate, how much you slept, maybe even how many cuddles you got was significant. Probably not, but maybe. And so there are a lot of other things that could be going on. And so that's going to be meaning that even if there's one line which is a nice simple relationship between, let's say, some collection of genes that we've identified, because if it was just one, then we wouldn't get this linear kind of continuous variation. Let's say there's a true relationship of how that affects height. There's still going to be all this randomness, which is causing these deviations. The fact that there are loads of different data points on either side of our trend. This means that if we changed our sample and the randomness changes in different samples, we're likely to get some kind of variation in what we estimate the gradient to be of the true relationship between them, and what we estimate the constant to be. Like, what would the height be if the collection of genes was 0 in this case? So we're likely to get some variation. So maybe I take a slightly different data set in which, I don't know if you can see that color that well. Let me change. Yep, okay, beautiful. So let's say I've got a slightly different data set that still overlaps a lot, but you're starting to see that this one might have a slightly different trend. So maybe this one's trend goes like this. So now I've got another potential value of B0 or beta 0. I've got another estimator of the gradient, which is a bit steeper. And then I could do it again, and I could get slightly different trend values again. And if I take enough data points, it's unlikely that things are going to vary that much, but you can see there's going to be some variation in what I estimate. And that's exactly what the standard error that I talked about last time is trying to measure. It's trying to capture. It's trying to say, well, how much would we expect our estimates to vary? And then that's interesting, because then we can see, well, how likely is it that the value is actually that much different from 0? Because if the value is not 0, but let's say there's a 30% likelihood that if the true value of how the genes were associated with height was 0, let's say there was a 30% probability that we would still get the estimator that we had. Then that's not that unlikely. So we don't really have any strong reason to think that it's not 0, and that we didn't just kind of roll the dice and randomly get this different value. It's not that weird. So it's a bit like if somebody says, hey, that guy can roller skate at 10 miles an hour, which seems quite plausible, and then we measure him and he's currently roller skating at 9.5 miles an hour. And then this other guy goes, well, look, that's less than 10. Aha, we've got him. And we're going to go, well, not really, because that's only half a mile an hour less. It's quite realistic that another time he will be going at 10. It's not that weird that he got that value. So we're not going to really treat that as evidence that he can't roller skate at 10 miles an hour. But let's say somebody goes, hey, this guy can roller skate at 10 miles an hour, and then he seems to be going all out at it, and he's only hitting 5 miles an hour. Well, one, that's quite bad. But more importantly for us, that's reason to think, that's kind of sus. That's kind of weird that he would, we said he could go up 10 miles an hour, and then here he is just going at 5. He looks like he's putting in a lot of effort. That's very unlikely if he could really go to 10. It's very unlikely that we'd be seeing what we're seeing. And that's the same here. What we want is we want it to be very unlikely. If the true effect is 0, we want it to be very unlikely that we're seeing the non-zero estimator that we're seeing. That we're seeing this alternative fit to the data. We want it to be unlikely. So typically, we say, hey, we want it to be less than 5% likely that it would be this far away from 0. That's a standard level that we use. So we want that to be less than a 1 in 20 chance. So that's kind of a susness threshold. That's a level at which we go, hey, it's really sus that the value is this extreme. And so we're actually going to take it as evidence that it's not 0 and that it is having an effect. So to reference, in my last video, one of the p-values, the probabilities, was 27%. So if the true relationship between, I think in this case it was house price times family type versus the number of children that people have, if the true relationship was 0, then there's a 27% chance that we would have seen the relationship in the data that we saw. That's not that unlikely. So therefore we go, there's probably nothing there, really. We don't have any good reason to think that there's anything there anyway. We're not. So what I just said a second ago is not strictly true. We're not saying there's probably not something there, but we are saying there's not enough reason to think that there's anything there. It's not sus. And so unless we have good reason to think otherwise, then there's probably nothing there. That's worth clarifying. So this is basically a hypothesis test on, is this thing having an effect? And a hypothesis test is a susness test. How sus is this? And that will decide whether or not we accept that it's not really having any effect, or whether we reject the idea that it's not having any effect and go, hey, we think this is having an effect here. And so in the data that I gave, there seemed to be a significant positive relationship between house prices and fertility. Now that probably wasn't causal. That was probably that house prices are linked with other things that help fertility. But it does seem to be evidence that, hey, there's a real relationship going on here, even though we didn't investigate enough to tell us exactly what was behind that relationship. So this is a bit of the statistical background about what we're actually doing when we're interpreting the results of our regressions. And there you have it.